It's really excited to be here. I started using Linux when I was after graduation in 2003, and it's really cool to be here to talk about RISC-V. So today I'm going to give you some insight about the chip design economics, because as being software people, it's sometimes really hard to grasp how bad the hardware industry is. So I'm going to do a bit of a rant about that. And then talk about why that doesn't work for the future. And then talk about how RISC-V is revolutionizing the hardware industry. So let's dive right into it. Can you put the slides on, please? Yes, thank you. So I'm truly amazed how fast the IoT, edge computing, machine learning field is changing. As a matter of fact, to support the computing needs of these growing markets, we must customize not only the software, but also the hardware as well, because general purpose hardware or chips will not deliver the performance that you need for these growing applications. So the alternative future that I kind of envision is that there's going to be lots and lots of different custom chips rather than having just a couple high volume general purpose chips. However, the current chip design economics are not meant for building lots of custom chips. They're really geared towards building general purpose, high volume chips. So what does that even mean? So look at the graph on the right. It is known that to build a modern chip, microprocessor in a 28 nanometer process technology node, it will take more than $100 million. And that's why less and less people can actually afford building these chips. And it takes a long time to actually put your product to market. So we talked about deploying in a week. It's earth-shattering hardware to build a chip in 18 months. That's considered earth-shattering. So to really make that formula work, what people do is spend a lot of money and have to sell a lot of those chips to make the economics work. And obviously, as you can see, that doesn't really work well for custom chips, because just inherently, you're not going to sell that many volumes of those chips, because you're going to build your custom chip for just your application. You might have small volume. You might have medium volume. So in order to really change the chip design economics to work for building lots and lots of different custom chips, I'm proposing that the hardware industry needs to copy the success of the software industry. So to make my point a bit more dramatic, I'm going to ask you a rhetorical question. How did Instagram turn into a billion-dollar company with only 13 employees? Did you get that? That's about $80 million worth of value per engineer. Conversely, have you ever heard of a billion-dollar hardware chip company with 13 employees? Probably not. So let's think about why. By answering why, I can hopefully give you some intuition on how we ought to change the hardware industry. So I got the tech stack of Instagram. As a matter of fact, I Googled it. People share these tech stacks in the software world. It's kind of not heard of in the hardware industry. So there's two things why I think Instagram worked with 13 employees to build $1 billion worth of value. First, they use a bunch of open source technology, as you can see here. That means that they put the 13 engineers working on the Instagram stack not on building the ground-up technology and reinventing the wheel like operating systems and compilers. They put those 13 engineers to work on the part that mattered to them, the value-added part, which in this case, it was the application logic to take photos and share them. And married that with the cloud infrastructure, the easy-to-use cloud infrastructure such as Amazon Web Services, Route 53, CloudFront, S3, obviously something like Google Cloud as well, but to deploy their application at scale, to touch millions of users, and to test out whether they had a market product fit. So compare that to a typical hardware chip company's tech stack. Can you think of any open source technology? Can you think of any kind of cloud infrastructure to deploy the hardware technologies at scale? In this case, that means to build a chip. Anything? Emacs. Oh, yes, Emacs is very important. Yes. To build chips, yes, Auto-Verilog and all that. So I'm here to report that we've been making a lot of progress here. So there's RISC-V. It's a free and open instruction set architecture, which I'll talk about. Also, companies like NVIDIA has started to open source their hardware technology. So they recently open sourced DLA, the Deep Learning Accelerator. It's an inference engine. And today, I'm going to talk about SiFive Cloud Services, which is a cloud infrastructure to deploy your hardware technology at scale. In this case, we are going to help you build your own custom chip very fast at an affordable price. So what is RISC-V? I'm compelled to ask how many people know RISC-V? Wow, OK, great. So RISC-V is a high-quality, license-free, royalty-free instruction set architecture. So Professor Dave Patterson at Berkeley has started 4 RISC projects in the 1980s. You can see all the chips on the below, RISC-1, RISC-2, RISC-3, RISC-4. RISC-V is a 5th-generation RISC design from UC Berkeley. I started the RISC-V project when I was a grad student at Berkeley in 2010, alongside my colleague and friend, Andrew Waterman, and our advisors, Chris Hasanovich and Dave Patterson. RISC-V is appropriate for all levels of computing. That means from your smallest microcontrollers to your embedded Linux device, all the way to the supercomputer HPC machines. RISC-V is experiencing a rapid uptake in both industry and academia. And it is supported by a growing software ecosystem. So RISC-V support for GCC, binutils, ulib, glibc, Zephyr, Linux, FreeBSD has all been upstream, thanks to your support. And we started a nonprofit RISC-V foundation to maintain the standard. And now we are at more than 100 members. So if you see your company's logo here, thank you very much for your support. If your company logo is not here, well, you're missing out big time. So I go back and I kind of talk about, to join the RISC-V Foundation to see what's going on. So thank you for your support. A quick note on NVIDIA's effort to open source their machine learning inference engine. So you see Jensen Huang, CEO of NVIDIA, at the stage at last year's GTC, is proudly announcing the Xavier DLA, that it's going to be open source. This DLA engine actually has been taped out in one of the Tegra chips that NVIDIA built. So what is DLA? It's a deep learning inference accelerator for IoT markets. It's scalable, highly configurable, and it supports a wide range of IoT devices. So kudos to NVIDIA. Thanks for doing this. And I would love to see more companies joining the open source hardware revolution. So I'm going to switch gears and talk a little bit about the SiFive's chip design services. So in order to really deploy your hardware idea at scale, you need to put that in a piece of silicon or a chip and have that built. So what is SiFive Chip Design Services? It's a cloud infrastructure to change the chip design experience to replicate that in a form of a website click or an API calls, just like how you would bring up your virtual data center today. You would not go buy machines. You would not go buy networking gear. Just sit and call some APIs to call your own virtual data center. So similar to that, we are building this cloud infrastructure to support chip building. So how does it work? So you log into the website on the upper right, and then you pick a template for your chip. So today we have 2 templates for building your own chip. The first template is called Freedom Everywhere. It's a low-power 32-bit microcontroller. It's manufactured in TSMC 180 nanometer, and it's good for IoT applications. The second template is called Freedom Unleashed. It's a high-performance 64-bit multi-core platform. It's manufactured in TSMC 28 nanometer, so it supports your coherent accelerators. And we have already onboard all the important peripherals, such as PCIe, DDR, and gigabit Ethernet. So the idea is that you don't need to work on onboarding all these important IPs onto the platform. We've already done the work to do that. So I envision that this platform will be good for embedded Linux applications. So after you selected these templates, then you can go on to a marketplace where all the third-party IPs have already been onboarded to our project templates. So today we have IPs from Rambus, Ultrasoft, FlexLogic, eMemory, Analog Bits, and ThinkSilicon. And they've already been onboarded onto our platform. So they will be available on the website. And on top of that, you can go and onboard additional open source hardware IPs, as well as your piece that matters to you, your customer IP, which is the value-added piece that you build. And then after a couple clicks away from the website or API calls away, then you'll get your own custom chip billions of them, just for your need. So in other words, we're trying to change the chip design experience into something like ordering pizza online. Actually, you go to Domino's.com, you put in your address, and then you pick a store, and then it turns out you can start building a pizza from scratch, or there's the so-called specialty pizzas, which, in my opinion, there are templated designs for your pizza. And then after that, you pick your toppings, and then you click the order button. You don't talk to people, and you get this progress bar. It says, preparation, baking, boxing, and then delivery. So think of that. Chip design will be something like that. The only difference is that chips will be a bit more expensive than pizza. So okay, let's dive in. Let's look at the Freedom Everywhere platform. It's a 32-bit low-power microcontroller platform. On the left, you can see the block diagram of the platform. At the heart, there is the SiFive E31 CPU, which runs at 320 megahertz. We support multiple power domains so that you can have your low-power standby mode. And the platform will also accept a wide range of clock inputs. So to demonstrate the platform, we've actually taken the platform ourselves, and we taped it out on TSMC 180 nanometer, and that's the chip on your right. That's the Freedom Everywhere 310, or the FE310 chip, manufactured in TSMC 180 nanometer, and it has a QFN 48 package. So the idea is that take the platform, look at it, and add or subtract the features that you need or you don't need. And also, you can come with your own piece of the hardware. Just plop that in and tell us a couple button clicks away, and you get your own microcontroller just built for your application. So a quick performance and power comparison for the FE310 chip. So we took 3 additional microcontrollers that were built in the same process technology node, TSMC 180 nanometer, and we did a comparison. So if you look at the Intel Curie module, it runs, the top speed of the CPU is 32 megahertz. And all the other ARM Cortex-based microcontrollers have a top speed of 48 or 16 megahertz. Compare that to our FE310 chip, which runs at a maximum speed of 320 megahertz. So we are 10x faster than Intel and 11x more performance than ARM. We also measured the power. It's 9x more power efficient than Intel and 2x more power efficient than ARM. So it's a pretty good platform. So we also put together Hi-Fi 1, an Arduino-compatible RISC-V development board, which has our FE310 chip here. We've sold 1,000 copies to more than 45 countries today. If you want your own, you can go to crowdsupply.com. It's $59. You can order it right away today. So jumping on to the second template, which is the Freedom Unleashed template, which is a 64-bit multi-core RISC-V Linux platform. If you look at the block diagram, on the left, you can see at the heart that there's the U54MC SiFive CPU, which runs at 1.5 gigahertz. It has 4 application cores, which are Linux capable, and 1 embedded core for housekeeping of the chip. We also have a chip-to-chip coherent link coming out of the platform, which we call ChipLink. The platform also has DDR3 and 4, gigabit Ethernet, and a bunch of peripherals. Similarly, we took the platform to demonstrate that it actually works. We took the platform and we actually built a chip. You see that on the right. That's the Freedom Unleashed 540 or the FU540. Comes in a flip chip BGA package, and it's also manufactured in TSMC 28. We put together Hi-Fi Unleashed, which is the world's first multi-core RISC-V Linux development board, which features the FU540. Comes with 8 gigabytes of DDR4 memory with ECC, gigabit Ethernet port, SPI flash, micro SD card, and also micro USB for debugging and serial communications. Also has an FMC connector for future expansion, so if you want to connect to PCI or USB, there will be an expansion I/O board with a South bridge on it. The early access units for March has all been sold out. If you want it at June, you can go order your own Hi-Fi Unleashed board at crowdsupply.com for $999. We have a bunch of software working on these platforms, thanks to your support. RISC-V support for binutils, GCC, newlib, glibc has all been upstreamed. RISC-V support for operating systems such as Zephyr, Linux, FreeBSD has all been upstreamed. RISC-V emulator ports for QEMU has been upstreamed. However, there's still some missing pieces, which I'm asking for your help. There's missing support for glibc 32-bit, also missing some Linux drivers. As a matter of fact, I have been told today that there are more projects that have already been upstreamed. This list is growing every day. And the RISC-V distribution ports are also in progress. Debian, Fedora, OpenEmbedded, OpenWRT, Gen 2 are all in progress to have RISC-V support. As a matter of fact, there's a talk today at 3 p.m. about RISC-V OpenEmbedded by Kim Raj. So if you're interested, I urge you to go to his talk. And I have to do a quick shout out for everyone who's been helping us out. This has truly been a big effort. People at SiFive, Berkeley, Red Hat, BlueSpec, Andes, thanks for your help. And we look forward to getting more help porting software to RISC-V. So I'm assuming by now you're all excited about RISC-V. So how do you get started? So we're super excited to have you experience RISC-V at this conference today, tomorrow, and the day after. So we brought a bunch of HiFi 1 boards and HiFi Unleashed boards, and we're going to throw a RISC-V hackathon. So it's going throughout the entire 3 days of the conference. It's at the 23rd floor of this hotel. It starts 10:30 a.m. every day. So after today, it's going to happen after all the keynote sessions this morning. So we have 3 challenges. And the prize for each challenge is you get to have a HiFi Unleashed board and $2,000 of cash. I'm just going to point out that nobody has gotten an HiFi Unleashed board because we haven't shipped it. So you'll be one of the first people to have the HiFi Unleashed board today. So the 3 challenges we have. The first one is HiFi 1. So turn HiFi 1 board into a USB mass storage that you connect to your computer. So you will have to port the USB 1.1 stack using GPIOs. And you'll be able to mount the flash on the board to your computer. The person who gets the highest speed writing and reading a single 1 megabyte block will win. The HiFi Unleashed challenge is to port a web browser to RISC-V. And the person who achieves the highest score running the Jetstream 1.1 browser benchmark will win. And the third category is to just come up with the coolest demo, which will be voted by the SiFive crew. So obviously, you don't need to stay all day long at the HiFi hackathon. You can pop in and out. If you're also interested in just experience RISC-V, you can stop by to play around with the board. There's also BOF tables. RISC-V Zephyr and RISC-V Linux drivers will be discussed at the 23rd floor, so please come. So for those who can't wait to go hack on the hardware, I have some good news for you. We've also open sourced the Freedom platform. So that means you can take the RISC-V Rocket CPU, which is open source, Tie-Link, the coherent chip interconnect, low-speed peripherals, high-speed Xilinx peripheral wrappers for DDR PCIe, and map that onto your own FPGA. So you can see on the top, that's the Freedom Everywhere platform mapped onto an FPGA. On the bottom, that's the Freedom Unleashed platform mapped onto an FPGA with some PCI cards. You can see Doom is also working on that. Unfortunately, there's some third-party IPs that has to kept closed source because of NDA reasons. You can get access to those by using the SiFive chip design services, however. So if you're interested, check out dev.sifive.com or SiFive's GitHub organization or FreeChip's GitHub organization. So to conclude, please join the RISC-V revolution. Open source has revolutionized software. Now it is hardware's turn. For software developers, thanks to your help, the RISC-V software ecosystem has been growing rapidly. So continue your work, help porting your favorite software projects to RISC-V. For system designers, I'm here to tell you that now you can afford a custom chip just built for your application. So start customizing SiFive Freedom platform and innovate at both the hardware and software level. So join us at the hackathon, BOF sessions, as well as our demo session. So this is multiplayer Quake 2 running on RISC-V connected to an x86 machine. So you're going to run Quake on RISC-V, run Quake on Intel, and you're going to shoot each other. So as a start, we're hiring aggressively too. So if you're interested in joining the next wave, and also visit sifive.com for more information. Thank you very much.